In this video, we're going to discuss a variant of the t-test in which the alternative hypothesis is directional, or also known as one-tailed. To begin, I think it would be useful to remind ourselves of the definition of the p-value. The p-value is a probability, right? And it's the probability of observing a test statistic at least as extreme as the one you observed. However, this is incomplete. This is under the assumption that the null hypothesis is true. And this calculation takes place slightly differently depending on the statement in the alternative hypothesis. Up to this point, we have seen what we would call non-directional or two-tailed t-tests. In these types of t-tests, the way the alternative hypothesis is stated is there a difference, not equal to. The p-value is the area in both tails of the t-distribution, and that's beyond plus or minus the test statistic. Because a two-tailed or non-directional t-test is testing if a difference exists in the population means, right, that difference can take place in two ways. Group 1 can be larger or group 2 can be larger. We're looking for a difference. When that test statistic is calculated, it could be negative, right? It could be positive. And that's also not entirely important with the classic alternative hypothesis here, depending on how you've structured your test statistic. But we're looking for that difference, and so the area is in both tails, right? So that p-value is both those areas added up. In a directional or a one-tailed t-test, the p-value would only be one of these tailed regions. So we have two versions of these. A directional, this example illustrates a left-tailed alternative hypothesis. Therefore, the p-value in a left-tailed test is the area to the left of the test statistic. The other version of a one-tailed or directional alternative hypothesis is when there is a greater than symbol. And this would be specifically referred to as a right-tailed alternative hypothesis. Therefore, the p-value would be the area to the right of the test statistic. With a directional t-test, that hypothesis needs to be formulated prior to collecting or looking at the data, right, in the hypothesis stage of research. That hypothesis should be founded on some expertise in the field, because we'll see in a moment here that it's possible to reject the null hypothesis with a directional alternative hypothesis, but not with a two-tailed alternative hypothesis, even though you're using the same data. As such, that could increase the chance of making a type 1 error. And in a moment, we're going to look at an example of how that could be. Let's take a look at this example in which we have two scenarios, and all the elements of these are the same with the exception of the formulation of the alternative hypothesis. So we're not calculating the test statistic here. I don't have a particular context to look at. I'm just cutting to the punchline. The only difference is the structure of the alternative hypothesis. Let's see how we would compute the p-value in these two scenarios and see how this could be problematic if we do not form a hypothesis with thoughtful prior consideration. In scenario 1 here, if this is a t-test, this is t distribution with 18 degrees of freedom, the test statistic was a 1.82. The p-value, because this is a right-tailed test, would be the area to the right. In scenario 2, the image for reference here is very similar, but because it's a two-tailed test, we look in the two tails. So negative 1.82 is also a useful reference here. And the p-value would be both of these tailed regions, two-tailed test. Let's use R to calculate those red shaded areas, the p-values in both of these scenarios. Remember, we want to find probability. Will we use the pt or the qt function? Think about it. One more thing before we cruise on over to R. In the second scenario here, remember, symmetry allows us to state that these two tailed regions are identical. So once we have found one of these regions, doesn't matter which one really, we can just double it and then we'll have the entire p-value. Let's go over to R. I have my screens organized here so I can look at my diagrams while I use R. Let's find the p-value for this scenario on the left, which is for a right-tailed test. We want the probability, so we need to use pt. The test statistic is a 1.82. That's our t-value. The degrees of freedom was 18. This is not correct yet. Remember, R would actually give us the area to the left of this tick mark. We don't want the area to the left, we want the area to the right. So what must we do to this pt function? 1 minus, right? Okay, so our p-value for the scenario on the left is 0.0427 approximately. Now let's consider the p-value for the two-tailed scenario on the right side. We have just found the area in the right tail, didn't we? 0.0427. That would also be the area in this left tail. So the p-value in scenario 2, we need to add both of those up. R, please do that for me. I'm going to take our previous result and multiply it by 2. But of course, I need to put our previous result in parentheses. Our answer should be about 0.08. Now let's state our conclusions to the t-tests in each of these scenarios. On scenario 1, with the directional t-test, notice if the p-value is bigger or smaller than alpha. Alpha is 0.05. Our p-value is about 0.042, so therefore our p-value is less than alpha, and our conclusion should then be to reject the null hypothesis. The way we would interpret that if we had some context here is that there is evidence that mu1 is greater than mu2. Now let's look at our two-tailed or non-directional t-test. To determine our conclusion, again, compare the p-value to alpha. Our p-value is about 0.085. And that is larger than 0.05. In this scenario, we would not reject the null hypothesis. Our interpretation of that is there is insufficient evidence or insufficient support for the statement in the alternative hypothesis, insufficient support that these two means are different, significantly different. As you can see in these two scenarios, with all the same quantitative values, we ended up with much different conclusions. And that was purely as a result of the formulation of the alternative hypothesis. So it's important to create your hypotheses based on sound reasoning, or else you could open yourself up to potentially making an error. Now, we don't know which one of these conclusions is the correct conclusion. If an error was made, the scenario on the left, because this resulted in a rejection of the null hypothesis, this could be a type 1 error. We don't know though. The scenario on the right here, because the conclusion was a non-rejection, this could be a type 2 error, but we don't know. I have one last comment to make, and it's a rhyme. Prepare for rhyme time. I know that there's all these relationships to keep in mind. One of the big relationships that I want you to remember is that we reject the null hypothesis when the p-value is small. My rhyme time: when the p-value is low, the null must go. When the p-value is low, the null must go. In the next video, we will do a complete example of a directional t-test.